My name is Mac Hyman. I was an undergraduate at Tulane 40 years ago. Then after getting my graduate degree in applied math and mathematical modeling, I went on and worked at Los Alamos National Lab for over 35 years. At that time I was head of the applied math group, and our group and the laboratory in general exist for one reason. Our national labs are to give scientific guidance on problems of national and international importance. Problems where you need teams of scientists from lots of different disciplines working for often decades to help guide policymakers, anything from preventing nuclear war to solving the energy crisis, dealing with climate change. That's where they run the big climate change simulations, as well as mitigating epidemics. Los Alamos hosts the International HIV/AIDS database for DNA. It's where vaccines are being designed to help stop the virus. When the anthrax attack came, Los Alamos was the place that had the sequences for anthrax. They could trace it back to find out where the bio threat came from. And so especially for terrorist events, and also the labs have played a critical role for decades. They're now starting to play a large role for natural disasters. When hurricanes shut out the lights across Louisiana, Texas, Florida, the national labs are where they have the large simulations on how you turn them back on again. Because you don't just flip a switch and all the power systems come up again. If you remember, it was about 10 years ago, one power station failed in the Northeast and knocked out the whole East Coast. And so to do these simulations on how to do this take decades to put together and to help guide essentially in policy decisions on how do you recover from natural disaster. And my role there for the last 20 years has been how can scientists help slow the spread of an epidemic, especially in a new emerging epidemic such as SARS, or a couple of years ago the H1N1 swine flu, when we didn't know how bad it was going to be or how to respond. In that case, we knew we had some vaccine, but not enough for everyone. Can we be more effective at stopping the epidemic if we're very careful on who gets the vaccine first, instead of doing it like we normally do the flu vaccine, that we give it to everyone? Okay. And during that time, the last 20 years, I've seen our capabilities grow from very simple little models, which you call ordinary differential equation models, 2 or 3 equations, which you can write down on the back of an envelope, to what they now can do is simulate tens of millions of people as individuals and watch an epidemic spread through a virtual environment and try experiments there that to find out what is most effective in, say, a very sophisticated simulated city or SimCity, and then take what we learned from these virtual worlds and then apply them to the real world to help guide us in fighting epidemics. And so when Nancy asked me to talk today, she asked me to kind of give a mixture of kind of how the field has matured in the last 20 years, as well as some cases where it's made a difference. So you as future decision makers can decide, maybe I could get a help from a large-scale simulation. Or if someone who runs a simulation comes in and say, I can solve your problem, whether or not you should trust them, which is just as important. So I was going to start with the very simplest model and kind of work my way up in complexity. All the models to simulate the spread of epidemics have the same form. We divide the population into essentially 3 categories. Those that are susceptible of being infected. And susceptible means that whatever the epidemic is, you're capable of getting the disease. So for instance, if you had the flu last year and this year flu is the same as last year, you wouldn't necessarily be in it. When H1N1 came, everyone was susceptible. When the HIV epidemic happened, everyone was susceptible. Then they get infected with some rate lambda into an infected class. And they're capable of infecting other susceptibles, and slowly they work over to this recovered or removed class. Removed if they die, recovered if they recover from the disease and then are immune to future infections. Okay? And now, we write these simple equations mathematically. They look linear, we know everything about it, but there's a huge amount of complexity hidden in these symbols. The susceptible population might be divided according to age, susceptibility, income, these type of things. And so we'll go through the different things that we can do here. Now, in all of these equations, the key factor, the nonlinearity, the determining part of the equation that decides how fast the epidemic is spread is something called the rate of acquiring an infection. So if you look at here, the susceptibles go to the infected at some rate lambda. Okay? Lambda is like number of people today per day that are infected. So if you have, you might have 10 people a day being infected or 100 people a day being infected. That'd be 10 times the rate of being infection going from 10 to 100. And in all these models, we can break this rate into 3 factors. The number of contacts that a person has. So if you're walking around the population, let's say, what's a contact? A contact is anything you do, that people do, that's capable of transmitting the infection. So if we were modeling the spread of flu, we're all in contact with each other in this room. Okay? If we're modeling the spread of HIV/AIDS, we wouldn't necessarily be in contact. It takes either a sexual contact or sharing an IV, through drug use. So we use this term contact in a very disease-specific way. Okay? Now, if we double our number of contacts, so if you say an infected person has 10 contacts per day, it spreads at some rate. If on average an infected person has 20 contacts per day, it spread twice as fast. They would infect twice as many people. So the rate of acquiring infection is proportional to the number of contacts. It's also proportional to the probability that the contact is infected. If you have 10 contacts a day, you could double it to 20 contacts a day. Doesn't matter, you won't get infected unless the person you're having contact with is infected. So if twice the fraction of the population is infected, the infection will spread twice as fast. Okay? So it's also proportional to that. And then the probability of infection per contact. Not every contact is equally likely to spread the disease. You know, if you meet someone for 5 minutes, it's probably a very small probability you'll get infected. But make that same infected person for 5 hours, there's probably a large probability that you're infected. So we have to worry about this. And so we estimate these 3 factors, and that's what gives us the rate. Okay? And we'll get into each of those factors in a lot more detail. The other key factor that goes into is what we call the threshold conditions. The threshold conditions is the tipping point for an epidemic. Okay? If we exceed the threshold condition and we introduce one infected person into a susceptible population, the epidemic will take off. If we're below the threshold condition, we introduce an infected person in it and it will die out. Okay? And we measure the tipping point, the threshold condition, typically by something called R0, our basic reproductive number. So basic reproductive number, we use the symbol R, and R at times 0, or R where means on average how many secondary people, how many people would a single infected person infect if they're entered into a susceptible population. So if on average an infected person infects 2 other people, those 2 people would infect 2 more people, those 4 people would infect each 2 more. So the epidemic would grow, 1, 2, 4, 8, 16, 32. It grows exponentially. And that exponent has to do with R0. So it's R0 to the nth power is how many people would be infected by the nth generation. Okay? So a lot of what we do is find out what is R0 for a particular disease, and what do we have to do to change to drive R0 down below 0. So that's essentially the heart of epidemiology. How do we drive R0 down to 0 for new infections? And R0 we can break into 3 factors again. One is the number of contacts per unit time. Again, if people have twice as many contacts, it spreads twice as fast. The probability of transmission per contact. And the last is the length of time a person is infectious. Someone's infected for 4 days is likely to infect twice as many people as someone's infected for only 2 days. And now by breaking it to these 3 factors, we can talk about mitigation to reduce each of the factors. So we can change behavior to reduce the number of contacts per unit time. We can either have people stay at home, we can close schools, We can shut down mass transit centers or people who congregate. We can reduce the probability of transmission per contact by either reducing the susceptibility of people by getting out vaccines, or reducing the infectiousness of people by increased hygiene, having them wash their hands, stay at home, wear a face mask. We can reduce the time of infection through treatment. So it tells us this is how we fight it. We actually go after each one of these terms. So one of the first things we do when a new epidemic comes out is we ask, how big is R naught? How much do we have to reduce it to stop this epidemic? And this came really to a head about 2 years ago when the H1N1 swine flu came out. At that time all we knew was that it was in Mexico there were increasingly number of cases, a large number of deaths, and we don't know how big of a threat it was. So the first thing we did was we calculated what R naught was, from real data. We took how many cases, and then we can, using that formula, we can estimate it. So this is in Canada. This is week 0 to the first 20 weeks of the epidemic. In Canada, you can't read this, but R naught comes about 1.35. Mexico, it came out to about 1.3. And Spain, about 1.4. And so R naught, it looks like, was only about 1.4. That means that each of those factors we only have to reduce by a small amount, okay? Okay, let's see. And one way to do it is by increasing or decreasing the fraction of the population that is capable of being infected by essentially through vaccines, okay? So we have to so we reduce it, so if R naught is equal to 1, the R naught we can reduce if we vaccinate half the people, then we reduce R naught by a factor of 2. Okay? So our new R naught is the old R naught times 1 minus the fraction of the population that's been vaccinated. So we can calculate how much of the population would have to vaccinate. Once we have R naught, then we know how much we have to vaccinate. So for H1N1, it was 1.4. So what do we multiply 1.4 by to get it down below 1? Okay? So 1.4 is 7/5. We have to take about, that's 5/7. 1 minus that, 2/7. We have to vaccinate about 30% of the population to stop the H1N1 epidemic. And so that's what CDC was thinking. How do we vaccinate at 30% of the population? And that's if it's all randomly mixing. Other diseases, it's different. So for diphtheria, R naught is 6 to 7. We have to vaccinate 85%. For measles, R naught can be as high as 18. This is why measles vaccination is mandatory, because we have to vaccinate over 90% of the population to keep R naught for measles down below 1. Smallpox, 6 to 7. We have to vaccinate around 83 to 85%. At least that's what we were vaccinating when we eradicated smallpox. So depending upon R naught, it tells how big the effort has to be, at least through vaccination, to stop the epidemic. Okay? So here are our equations again, and you realize quickly, well, one of the first things, what mathematicians do when we write down equations, we ask, is our simple model, what's the most important aspect of this model that we're leaving out? If we want to make it more complicated, what do we need to add in? Okay? And for this model, probably the most important thing is that not everyone is in the same infectivity during the course of the disease. Plus their activity levels change. So this would be for, I think this is for flu. Yeah, this is for flu. So you're infected with the flu. The solid circles are how infectious you are, how much virus you're shedding off to the environment. So after you've been infected with the flu for a day, you're shedding off lots of virus. You're pretty infectious. Not greatly infectious, but you're pretty infectious. This is how bad you feel, the malaise. You don't feel too bad. Okay? So you go to school, you go to work, you infect a bunch of people. The next day, you feel much worse, and you're also much more infectious. Hopefully you're staying home this day. If you don't, you're likely to infect twice as many people as you did the day before, because you're shedding twice as much virus. Now you feel really bad. Now you better be staying home, otherwise your coworkers should kick you out. You're not actually as infectious. and then you stay home for a few days. Oh, I'm feeling pretty good now after about the 5th or 6th day. You go back to work or school where you're still infectious at that point. Okay? So within the model, we need to incorporate both a time-dependent change of how infectious you are after you get infected, as well as how your behavior might change, depending on how bad you feel. And the way we do that is we take this infected stage and we break it into many, many stages. So stage 1, you're infected, you're infectious, but you don't feel bad. You infect, say, people at some rate. Next day, you feel really bad. Half these people stay home. The other people have to go to work. The next day, nearly everyone stays home, but they're highly infectious. They infect family members. Okay? So we can write down the differential equations for this, and mathematicians love doing this, and we can solve analytically for the R-naughts, and we get a weighted average of all the different stages, and mathematicians, we play our games, we write papers, and we write theorems, and we have a good time. And we go back and say, okay, now what's the next most important thing that we need to know? Well, not everybody has the same level of infectivity when they get infected. Some people are highly infectious. Maybe they have a poor immune system, and so they really shed a lot of virus. Maybe they have, other people are not infectious at all. Maybe they're very fastidious. They wash their hands all the time and keep themselves clean, wear a face mask. Other people never wash their hands. Hi, how you doing? So we better have somehow distribute the population in levels of infectivity. Okay? That's very important for HIV/AIDS, where we had the activity levels were quite different. One of the first people that got infected with HIV/AIDS was an airline steward. Visit the bathhouses in New York, San Francisco, flying back and forth across the country. Essentially, the HIV/AIDS epidemic took off much, much faster than it would have as if you'd been someone in an old folks' home. So we better account for these different levels in the model. And again, we can calculate what the R-naught is analytically and do our mathematics and write papers and understand what factors go into this R-naught, so we know how to go after which of these groups. And this is one of the highlights in math where it had a big impact in stopping the spread of gonorrhea, to realize how important what they call the core group is. Now, with gonorrhea, there's usually, if it's sustained, often there's a small group of people that are keeping the fires alive. It might be a prostitute ring, it could be anything. It could be someone who's doesn't even know that they're infected, but still are infectious. And so there's a lot of effort to show that this is how important it is to say, identify that group of highly infectious people. And the models, and the mathematical models really highlighted that. In hindsight, it's obvious. But in foresight, they were just treating the people as they came in. And the model said, no, you got to find out, go back, contact trace. But when you find someone infected, find out who they had sex with, test them, and keep going back and see if all the fingers point to the same group of people, and then treat those people. Okay? Then we can say, well, it's not one or the other. Or we may want to add age, 1-year-olds, 2-year-olds, 3-year-olds. If we're doing something like malaria, age is very important because the susceptibility of the population. Everyone's born susceptible. They get malaria at a young age. Death rate is much higher in the young than the older. They fight it off, and so we better put in age. We better do this, and we can solve these mathematically and numerically. And we wrote papers, and I've got 5 or 6 papers on this and theorems, and realized that, wait a minute, we're really getting lost in the mathematical equation land here. We really want to look at the forest. We want to see from high above how the epidemic is spreading. And when you look at the forest, you can look at the forest. It's okay to look at the trees. And at some point, we start looking at the bark and getting lost in the details when we really need to back up and say, maybe this isn't the next most important thing to go in the model. Maybe it's something else. Okay? Maybe instead of putting in age, it's more important where people live. I mean, you're going to infect people. If you're infected, you're going to infect other people in New Orleans. You're not going to infect people in Seattle. So maybe we better put space in the models. So we start putting space. And we went back to historical records, and this is the pandemic of 1781. Okay? We started in the Russian Empire, and this is in December. It was here. January, February, March, April. It was a diffusion wave across Europe. And we've got historical records, and this was a beautiful book written by Jerry Pyle, We went back all the way back through the 16, 17, 1800s, looking at old church records to find out when the epidemic arrived. And you can calculate the speed, we write diffusion equations and stuff. And the speed of the epidemic is about horseback speed. Okay? And so we can model these. We looked at what the records show for 100 years later. This is 1847, 1848, the epidemic. Again, it started in the Russian Empire and also the Ottoman Empire. September, October, November, December, it's a wave coming across. And then something really strange happened in Central Europe. It shot up in the middle of Europe and then started spreading out. So October, it looks like it's spreading this way and that way. In November and December, it's spreading outward. Any thoughts why this is so different than it was 100 years ago? Before?
Folks in Spain didn't have the immunity that the other...
Well, that's a good guess, immunity. It may have happened the year before, but it's still a strange pattern. They just put in the railroad to Central Europe. And so the thought is that someone probably took a boat across the Mediterranean, landed in France, took the railroad, and infected people all along the railroad line. And then it spreads out from the railroad line. If we look at modern day epidemics, they happen almost simultaneously across the whole country. So this is the Hong Kong flu epidemic of 67, 68, which I hold not very fond memories. I had the Hong Kong flu. And I got it late in the season, which made it worse because it was the junior, senior prom, and Jerry Lee Lewis was playing. I've still never heard Jerry Lee Lewis. My girlfriend went with my best friend. That was the last I saw of my girlfriend. This epidemic had great repercussions on my life. But you can see instantly it started in these major cities. You know, here's Houston, this is Baton Rouge, New Orleans area, Savannah, and then spread out as a diffusion wave from the cities. Okay? Now it's not the railroads, it's the airlines. So very quickly it spread across the whole U.S. Okay?
Why do you think California and the Midwest wasn't touched?
I'm not sure. Maybe the sunny California.
Yeah.
Here it is the next year. California is still not off. But the map looks very, very different from year to year. And this is your answer about susceptibility is different. Because the people that got the disease the first season didn't get the disease the second season because they had immunity to it. Okay? So if we want to look at the spread of seasonal flu, our models better have susceptibility or immunity built into the models. Okay? So I had a summer student. So when I was at Los Alamos, I ran a summer program for many, many years. In fact, Roz was there for a couple. Were you there when Tara LaForce was there? Right after she was there. This was an undergraduate student looking for a summer project and decided, well, let's see if we can apply a simple SIR model to the spread of the flu across the U.S. Okay? He said, well, we better put in partial immunity. So instead of SIR, because you know, if not only immune, well, you don't really lose immunity to the flu, but every year the virus itself drifts. So you're immune to that particular strain of the flu that you were infected with, but the next year it's going to be slightly different, and the year after that will be slightly different. So we have this partial immunity thing. So you get infected, recovered, and then with some slow rate, you lose some of your immunity to the current circulating flu. Okay? And let's take the U.S. and we'll take the major cities and we'll connect them on a graph. Okay? So in every city, we took the population of that city. I went to the Department of the Census and got the population of metropolitan areas. Then we took the airline data. She went to the Department of Transportation to find out how many people flew every day between the different cities. And we connected, so here are the cities with an SIRP model, and then we had people flying back and forth. And then let's start an epidemic and see how it spreads across the US. And so, let's even do better than that. Let's take influenza data and see if we can match it to influenza data. And so to do that, first this is how many people, say, fly from Seattle to Los Angeles every day, 3,167. So we got the connectivity. When all the dust settles, we had 33 cities, 4 equations per city. So that's, what is that? That's 130 some equations. And And we had two unknowns that we didn't know. One of the unknown is, on average, how many people does someone have contact with per day in a city? Okay? And that one we can't separate with what's the probability of infection per contact. We didn't know that either. But the two of those are always multiplied together. So that was one unknown. What's the product of the number of contacts times the probability of infection per contact? And we also didn't know how much more infectious the flu was in the winter than the summer. All we knew was that it is more infectious in the winter than the summer, but we didn't know how much. So we had to fit the model to data to find out what those parameters were. Okay. So when we fit it to Seattle-Tacoma, what we called the risk parameter, which is a product of that infectivity and the contact, came out to be 408. And infectiousness, it was only about 1 or 2% more infectious in the winter than the summer, which really surprised us. We fit the parameters in Houston and Chicago, and wherever we fit it, the risk was about the same, which gave us the idea that we, instead of fitting the risk for every city, we just needed to fit one parameter over all the cities. And so we fit it over all the cities and came out with a number about 400. And we also fit the infectivity, how much more infectious it is in the winter than the summer across all the cities. So now we had 140 equations and we fit two parameters, and let's see how well we can reproduce the data. So we got the data from the CDC. Now CDC doesn't keep flu data. They keep data on upper respiratory distress. And so we made the assumption that a fraction of the upper respiratory distress cases came from flu, and that fraction was the same. We don't know what that fraction is. We probably could find it out. But then we fit the data. So the really noisy data is data, and the smooth curve is the model being fit. So these are thousands of cases per week. So this is 200 cases per week and 1.2 thousand. So 1,200 cases per week in New York City. And it goes through the data pretty well. Looks like they had a really bad year here. They had a good year here. Denver, that's about 150 cases per week. Denver had a bad year in 1998. Chicago, it fit about 500 cases per week. It fit all the data pretty well. We're very happy. And the idea is that when the number of cases are above what we predict, we say, aha, something's going on. We see if we can find out what it is. Or if we have a mitigation, we hope to see the number of cases drop below. You know, like we have a campaign that everyone in school wipe their desk and wash their hands 3 times a day. Let's see if it goes below the number of expected cases. That's what we were hoping to get out of the model. And it looked like we were doing pretty well, that we could say, aha, this is a bad year. I wonder what happened there. And we started looking closer at some of the cities. In Houston, we were predicting the epidemic is down here, but it was about 300 or 280 cases per week, but it seemed like it was about 400. You know what was wrong? So I was convinced there was a bug in the code or the data. So we dug it and we could not find it. Washington, we were predicting it around 330 per week, and the data showed less than 100. In Miami, we were predicting up here, we don't know what the heck happened, you know. So we, after weeks of trying to find the bug in the code, to go through the data, we finally called the Centers for Disease Control in Atlanta and said, we don't understand what's going on in the influenza branch. And the head of the influenza branch said, well, Houston is our best city. They get every case, they go out and phone call, they are just dogged at finding out how many people are sick. And if you're saying that from fitting the other cities, you're predicting here, but this is their data, this is an estimate of the under-prediction of the other cities. That's the number we've been wanting to know. Because yeah, New York is sending in this data, but that's reported data. The real data is probably somewhere up here, because they don't get the cases in New York like they do in Houston. So this is an estimate of the under-reporting. That's something that's really, thank you. That's a great number to have. Washington, well, Washington never sends us any data. You know, no matter what we do, we beat on them, we call them. Now, at least your model gives us an estimate of what the number of cases actually are in Washington. So, although we don't have the data from them, at least we can have an estimate of what that data would have been as if they had bothered to send it in. Okay, so we felt really good. So she said, this is really, thanks. We really appreciate this data. Miami, you can't explain Miami. And she said, well, a lot of the cities like Washington and Miami weren't reporting the data because they didn't have the budget. So we had a call for proposals, and we funded 6 cities in 1999 to start sending in data. And Miami was one of the cities, and when they sent in the data, we're really thrilled that the data they sent in matches your model. And they said, okay, what were the other 6 cities? Because we hadn't necessarily included them. And she said, well, it's Cleveland, Dallas, Detroit, Seattle, and every one of them, the model picked up right where the data was coming in. So we were just thrilled. And we told her that, you know, she didn't need to fund them, she could have sent us the money, we could have given her the data. We can give her the data for the next 3 years even. So this is an example of an undergraduate math student looking for a summer project. They used a very simple model that was able to determine some, essentially help them fill in data they didn't have. That's one thing these mathematical models do. They take the data you do have, and for the model to be internally consistent, they give you estimates on the data that you don't have. Because it forces this structure on the data. Okay? Then we can use it for other things. Since we have the airline data in it, we can say, what happens if a new disease comes in, like SARS? And we have 1,000 cases of SARS in New York City. How quickly will it spread across the whole US? And so Tara put it in her model, and very quickly it comes in. Within just a couple of years, you can't even tell that it started in one city. It shows how fully mixed we are across the whole US. Okay? Now, another area where we've done, especially in the last couple of years, we put a lot of effort in modeling. It's not just the spread among diseases among people, but the spread of diseases among animals. Okay?